Hello everyone. So this is part 2 of the series of videos covering signals in Linux kernel. So in the part 1 we discuss a little bit about the introduction, what are signals and what they're used for, the significance, the sources of signals, where and why they're generated, and then we covered the generation of asynchronous signals, the code path that it goes through, and how they are basically delivered to the added to the process's structure so that it can pick it up when they are ready. Now this is the second part of the video series where we'll be covering the signal generation for the synchronous types of signals, and then we'll also be covering the delivery for both asynchronous and signals because a large chunk of that code and processing is the same. So let's dive right in. Right, so as discussed in the introduction, synchronous signals are usually generated by errors, right? These errors possibly resulting in traps. As an example, we can see the code for two common exception interrupts. We will see basically right now maybe divide by zero, dereferencing, and null pointer, and both of them trigger synchronous signal delivery to the process, which causes the error. Right, and as I mentioned, these are the types of signals which are generated, delivered, and handled at the same time, as compared to the asynchronous signals which we had discussed in the part 1 of the video, where they are generated and delivered, but they are basically picked up and handled at different times by the processes to which the signal is delivered. Right, so we will start with this interrupt descriptor table because, as I mentioned, synchronous signals, one of the ways they're generated is through traps or errors that a process or a program runs into. Right, and when that happens, this IDT function from this IDT is triggered. So we are going to basically look into two examples here. One of them may divide by zero, and another one is overflow, right? And you see this is the macro which basically defines the interrupt descriptor table entries, and we will not look into how they're initialized, but just to add a reference here in the video, these are initialized during the init process of the kernel. The call chain is here. When you can look into it, it's like starting from start kernel to trap initialization to IDT setup traps, and there's a whole array of this table which basically defines which function would be called and for which trap or error. You can go ahead and look into the details, but we'll not be covering that here. Right, so let's pick one of them and expand the macro and see what we get. Right, so we have picked up one for this overflow, and when we expand we get this piece of code. The first is the prototype, second is the function exec overflow, and then this is how it looks. It has basically a little bit of instrumentation in the beginning, and there's one function call which is basically two function calls which is important, the underscore exec overflow, and another one that's important is at the end, which is a IRQ entry exit. So as I mentioned, this is a synchronous signal, hence first they are generated, and this generation is handled through this underscore exec overflow, and then they're delivered at the same time, and the delivery is basically handled by this IRQ entry exit. So you see this definition of exec underscore overflow, which basically calls to error trap, and this do error trap. These are very small functions, and they call one after the other. The do error trap calls do trap, and then it calls as force sig, which initializes the struct kernel siginfo, which we also saw in the part 1 of the series for the synchronous type of signals. For synchronous, the initialization of this siginfo structure is done here, and this basically looks very similar if you had seen the first video where it puts sig number equals, first it clears the structure, then it puts sig number sig, error number 0, and this is where you would see the difference. For the asynchronous one, since it was coming from a system call called from user land process, the SI code here was SI underscore user. This is a synchronous signal resulting as a from a trap from the kernel itself, hence the SI code here is SI underscore kernel. So after everything is initialized, it calls this function force underscore sig underscore info. This function calls force sig info to task, which then lands into this function called send underscore signal underscore locked. And this is how they look. And at this point, we're going to stop here because send signal locked is the exact same function which the asynchronous signal generation also uses for its processing, and we have already covered that in part 1. So basically what has happening is synchronous and asynchronous signal generation starts at different points, but then it lands into the same send signal locked. So if you want to just cover the synchronous signal generation, then you can watch the video till here, then jump to the part 1 of the series, start looking at the point where I start discussing the send underscore signal underscore locked, and then come back here for the next part, which is the delivery. Right, so after this we're basically gonna start jumping to the signal delivery part, and first we're gonna cover the synchronous signal delivery, and we cover it to a point, and then basically see that the asynchronous signal delivery also ends up at the same point, and the processing basically happens similarly for this both. It'll get a little clearer once we get into the code, right? So now the signal has been generated, and it has been added to the sig queue of the task pending structure. You would know what I'm talking about if you would have seen the first video of the series. And coming back to the IDT, as I mentioned, we just covered the exec overflow, and now it's time for delivery. And for synchronous, it's happening right next after that. After the instrumentation, you can see there's a function called IRQ entry exit, and this function basically calls IRQ entry exit to user mode, which then calls exit to user mode prepare. And this again is a common function here. You will see what we're talking about. We'll stop here, and then we'll come back to this when we finish the asynchronous signal delivery. Right, let's start with the asynchronous signal delivery. We will come back to this older function exit to user mode prepare, and then we will see how the signal delivery is handled for both synchronous and asynchronous one. Right, so these are asynchronous signals are handled later at a different point as from the time it is generated and delivered, right? So these are generally delivered when processes are moving from kernel to user mode. And one of the times that happens is when finishing a system call. So the entry point for a system call looks like something like this, right? It's for for an x86 64-bit system, and you can look at it. It's in a file called arc x86 entry common c. If you're interested in looking into a more detailed view where system call parameters are copied to registers and this function is called from assembly code, then take a look at this file called arc slash x86 slash entry underscore 64.s. Right, so you see that the function was calling underscore underscore syscall exit to user mode work in the end, which then calls this exit to user mode prepare. Right, and if you just recall that this was the place where we stopped previously, so it's both of the signal delivery for synchronous and asynchronous is basically coming to the same function called exit to user mode prepare. For the synchronous one, it starts basically from IRQ entry exit, which is from an macro generated IDT table function. For asynchronous is right after a system call has been completed, and it's through the syscall exit to user mode work, and it lands up into this function exit to user mode prepare. So let's dive into this common function and see further processing, which basically covers the signal delivery for both asynchronous and synchronous. Right, so this function exit to user mode prepare, the first thing it does is checks if there is signal pending or not. Right, and it does that by checking the thread flags against the stiff sig pending, which if you recall, we covered in the first part of the video is this flag is set in the end in the function called complete signal right after adding the signal queue to the list of task pending queue structure, right? And if there is a, a signal pending which is basically notified by this flag, then this exit to user mode loop is called. So this function exit to user mode loop, it's a simple one which has a loop which basically iteratively checks whether tifsic pending is set or not, and then it calls this arc do underscore signal or restart. So this function basically does two big things. It first calls get signal to pick up the next signal from the SIG structure, right? So the function get signal then goes into a loop and checks whether there is a synchronous signal or not first through the function called dequeue synchronous signal, and it regards synchronous signals as more important since they're generated by instructions ending from error like divide by zero trap. If there are no synchronous signals, then the function dequeue signal is called, which checks for other signals, basically asynchronous ones. So when a signal is found, its respective handler is taken from the task structure's SIG hand member, and then it is used later, we will see. So once this signal has been found, either synchronous or desynchronous one, you can see that the structure here that is being used to basically dequeue the signal and keep it is this called struct k signal, and it has the another member called struct k underscore sig action, which is basically the one which is storing the sig hand structure for the handler for the particular signal which has been dequeued, and that is basically used to call that handler to process the signal in the end. So as I said, after getting the signal from the queue, either synchronous or asynchronous one, the next thing that is done is the handle signal function is called. So this function basically does the main setup. It calls functions that does the main setup for invocation of the signal handler that we just saw, and this is done by these two calling chains called setup rt frame, which then calls underscore underscore setup rt frame. RT here stands for real time, and this was added to support an enlarge sig set underscore t type for real time signals. This was added sometime in the Linux kernel. I don't remember the version, but previous to that, just with no RT functions were used, and you can still find it in the kernel code. Just basically setup underscore frame functions. One more thing you would notice is that once you're looking into this underscore underscore setup RT frame, is that it has two different versions, one for 32-bit and one for 64-bit. They are basically in different portions of if def macros, and that is because obviously this is the one which is setting the process frame, and the size of the frame would be different for different bit versions, architectures, and etc. These also have different versions for different architectures, but yeah, we will basically be looking to the x86 one. So now we're going to dive into this underscore underscore setup RT frame function, and the code here is a little bit complicated, right? And basically to understand without the context of frame structures, CPU registers, and such, and it's a little frankly, I do not understand completely myself. There are pieces that I've picked up to basically tie everything together to understand how the signal handler is invoked and how the basic code execution jumps back to the user mode. For a more detailed session about stack frames and registers, we may have a session somewhere in the future, but let's try to understand the bits that are important here for us right now. Right, so I've broken down just lines of code from this function to get a basic understanding of what's happening here. Right, so first call here you see is the function get sig frame, which basically gets the current processor stack frame, and it creates a new signal frame and then inserts it over the current processor stack frame. And then what it does is it adjusts the register stack pointer accordingly. So it makes the stack pointer register point to the new signal frame that has been created. Right, this is the first thing that get sig frame does. After that, the pointed, so you can see that the adjusting of stack pointer is basically done in the last line. Get sig frame basically creates the signal frame, but it does not update the SP. Before doing that, the current processor stack pointer is basically stored in the second line. You see here unsafe save all stack, which is basically where your current frame for current processor stack pointer is saved into this frames underscore stack. After that, what happens is this frame p ret code is a place basically which stores the re-entry after the signal handler is done, and that is updated with this ka.sa.sa restorer, and this is supposed to basically be called by something called signal trampoline, which we'll see in the next slide. Once that those things are done, then the two registers are updated. Basically, the instruction pointer is directly updated to the signal handler where the signal processing is done for that specific signal, and then the stack pointer, as I just mentioned, is updated by to the newly created stack frame. And with this, the whole setup is done. Right after this is returned, the process execution would start with the new instruction pointer, which basically is the signal handler, as we see, and the code needed for that, the data needed for that, is already present in the new sig frame that was created, and the stack point is basically already pointing to that newly created frame. So everything is set up, and after this, the signal handler will start executing. Right, once the signal handler completes execution, it has to return back, right? So after execution of the signal handler, the code has to return back to the user space, right? Now the kernel arranges this return, right? Upon return from the signal handler, control passes to a piece of code, user space code commonly called the signal trampoline, right? And the signal trampoline then in return calls the sig return code, and for 64-bit system, this is called rt underscore sig return. Right, and it's basically a system call, and this is how it looks like. The relevant piece of code here is this restore alt stack, relevant for us. So the part about signal trampoline is a little unclear here. So on contemporary Linux systems, depending on the architecture, the signal trampoline code lives either in the VDSO or in the C library, right? In the latter case, the C library's sig action wrapper function informs the kernel of the location of the trampoline code by placing its address in the SA underscore restorer field of the sig action structure. So if you recall in our previous slide, that is what we were using, the SA underscore restorer, and we were using that to basically put it into the frame pret code. And that's where the code would start executing after the signal handler has completed its execution. And now that all that is needed is the user's stack that was stored, and as you remember, it was stored in this uc underscore stack, and this restore alt stack function is basically called with this uc stack, with where the user space uh, uh, frame or stack was stored before the signal handler was called, and this is then used to reset the stack pointer, and now everything is set for the execution to return back to the user space after the signal handler has been executed. Right, this marks the end of signal delivery and processing, and this is where we stop here. Thank you for joining, everyone, and yeah, we will probably be doing a third session about user-defined handlers and the code that basically processes that kind of work. Thank you. Please like and share it, and follow us on LinkedIn for more sessions. Reach out to us if you want some specific topics to be covered. Thank you.